Dear friends, welcome to a lecture of Riemann Integral. We are studying fundamental theorems of calculus. In this lecture, we shall study the next fundamental theorem of calculus, which is theorem of integration by substitution. Already we are using this method to obtain integration by substitution. Now we will prove the theorem which I have written as theorem number 10 in serial order. Theorems are numbered in this chapter from first. So, this is in serial order theorem number 10. Let phi be a real valued function on the closed bounded interval a to b such that phi dash derivative of phi is continuous on the closed bounded interval a b. Let further capital A is equal to phi of a, capital B is equal to phi of b. Then if f is continuous on this interval, that is the image of this interval under phi of a to b interval, then we have integral a to b f of x dx, integral from capital A to capital B is equal to integral from small a to small b f of phi of u, phi dash of u du. So, this is the theorem that we have to prove. We are already using this method of substitution. That means here actually the substitution is x is equal to phi of u. Then the integrand becomes f of phi of u into dx becomes phi dash of u into du. And these are the new limits with respect to u. This is the integration with respect to x, and the integration with respect to x is changed to integration with respect to u by the method of substitution. Now we shall prove the theorem. So, first we shall consider f is, since f is continuous, it is given, since f is continuous, on this interval phi of a comma b, interval a comma b. Actually, what is the meaning of this phi of phi image of the closed interval a to b? That means this will be the closed interval phi of a to phi of b. From a to b, its phi image is taken. So, phi of a, the interval will be, image of this will be the closed interval phi a to phi b, and the function is continuous on this interval. There is, by this theorem 6, or which is the first fundamental theorem of calculus, we have proved. Because the function is continuous, there exists a function. There is a function f of x, or there is f of x, such that derivative of that f of x, capital F of x, derivative of capital F of x is equal to small f of x. Because f is continuous means f is Riemann integrable, and because it is Riemann integrable, there exists a function capital F whose derivative is small f, and here x belongs to this interval phi image of interval a to b, and we may assume this as 1. Now further, so suppose capital G of u, we consider a function capital G of u as capital F in terms of this capital F function, capital F of phi of u, and here this function of u, and u will be in the interval a to b. So, that means a is less than or equal to u is less than or equal to b, means u belongs to the interval, closed interval a to b, and we may assume this as second statement, and we now differentiate this capital G using the chain rule. So, by chain rule, so we have what will be the derivative of G with respect to u, G dash of u, and the chain rule, this is a composite function capital F and phi. So, the chain rule is derivative of the outer function, that is capital F, and that will be f dash of phi of u into derivative of inner function, that is phi dash of u. So, this is the derivative by the chain rule, and further here what we have is capital F dash is small f. So, this will be small f of phi of u into phi dash of u, and again u is between a to b, or in the interval a to b. So, thus we have g dash of u is this. Now we apply the second fundamental theorem of calculus. That means if the derivative of g is equal to this right side, then the integral of right side is equal to g of u only. So, by theorem 9, this is second fundamental theorem of calculus. You may refer these theorems, we are earlier proved. Theorem 9, we have derivative of the left side function is the right side, then integral of this. So, integration of this function with respect to u is between a to b. So, integral from small a to small b, f of phi of u into phi dash of u with respect to u du. This is equal to integral of g dash u, that is from integral from a to b g dash of u. Or now we know the integral of g dash u is g u, and the upper limit is for g is b and the lower limit for g is a, and therefore this will be, this is equal to g of b, that is, so this will be equal to g of b minus g of a, and then so this is further equal to, so we have this as the left side, g of b. Now you see this second, g of u is f of phi of u, and therefore g of b will be capital F of phi of b, and g of a will be capital F by this relation. G of a is capital F, wherever u is there we have to write a, capital F phi of a. This is by 2, and again capital F of phi of b minus capital F of phi of a will be as integral. So, this I shall write in terms of integral. So, one more step I shall write here. This is integral, but what is see before that, what is in phi of b? Phi of b we are given as capital B, and therefore this is capital F of b, capital B, f of capital B, and minus f of capital A. So, this is the expression. Now, this we will write as see, I am writing here this step f b minus f a, that is exactly by the same theorem, theorem 9, integral from a to b f dash of x dx. So, by theorem 9, that is second fundamental theorem of calculus, and that means integral of f dash is f and the upper limit is b. So, it will be exactly equal to f b minus f of a. But what is f dash of x? F dash of x is f of x, that is why I have kept this statement, and therefore, this is integral a to b f of x dx. This is by 1. And thus, we have started with this right side. We have started with this right side, and we have expressed these terms, and finally, we get it is equal to integral a to b f of x dx, which is our left side, and this proves the theorem. So, this proves the theorem. We have proved integral a to b this f of phi of u into phi dash of u into du is equal to integral a to b f of x dx. So, this proves the theorem. Thus, we have proved the theorem, which is a theorem of integration by substitution. Now, we will consider an example to illustrate this theorem. Example is evaluate the integral I is equal to integral 0 to 2 under root 4 minus x square into dx. We shall evaluate this integral using this method. This is our left side integral, integral capital A to capital B f of x dx. So, here what is capital A is 0, capital B is 2, and f of x is equal to under root 4 minus x square, and we use the substitution as put phi of u is equal to 2 sin u. This is actually our x value. Put x is equal to phi of u is equal to 2 sin u, and that is our substitution we have selected. And what we require is again phi dash of u, and therefore what will be phi dash of u? Derivative of 2 sin u, we know it is 2 cos u. And further we have to get the new limits, small a and b. So what is capital A is phi of a. Now capital A is equal to phi of a implies what is capital A is 0, and what is phi of a? Phi of a from this is 2 sin a, that is phi of a we have the lower limit, and which is equal to 2 sin u. 0 is equal to 2 sin u, and from that we will get the value of u, or that can be written as a. Phi of a is 2 sin a. So what is the value of a from this? Sin a is 0, so therefore a is also 0. So this implies a is 0. Now b is phi of b. See this, b is equal to phi of b, and this implies what is capital B we have noted as 2. 2 is equal to, and phi of b, that is 2 sin b. Phi of b is 2 sin b. So this implies sin b is equal to 1, and that means b is equal to pi by 2. So thus the values of a and b are 0 to pi by 2, and therefore now this integral transforms to. So therefore integral I is equal to, therefore by theorem 10, what is the integral is originally, that is I. So we directly write I is equal to integral. This is the left side integral, that is 0 to 2 f of x dx, and now we are writing the new integral in this form, integral small a to small b, and that is 0 to pi by 2. 0 to pi by 2 under root, that is phi of f of phi of u, and f of phi of u will be, f is this, and phi u is 2 sin u. So f of 2 sin u, that means root of 4 minus x is 2 sin u whole square into phi dash of u. Phi dash u is 2 cos u into du. Now this can be simplified. So this is equal to, now see here is a 4 minus 4 sin square u, and that 4 can be written outside the radical sign, and root of 4 is 2. So this will be 2, and this 2 becomes 4. I shall write it like this, 0 to pi by 2, you can check. And what remains in root is 1 minus sin square u, and 1 minus sin square u is again cos square u, and root of cos square u is cos u. So I shall write directly, this is cos u and this is cos u, that will be cos square u. You shall verify this. And to evaluate this integral, we should use a trigonometric formula. Integral 0 to pi by 2, cos square u is 1 plus cos 2u divided by 2. This is formula from trigonometry, and into du. Now we can take this half outside the integral. We will now using the theorems that we have proved. So this is a constant that is lambda. Integral of lambda times fx is lambda into integral of f of x, and that means this constant can be written outside the integral, and that will be 4 by 2, which is 2. 2 integral 0 to pi by 2, and what remains inside the integral is 1 plus cos 2u into du, and that further is written as, so I shall write here, this is equal to 2. Now we can see, we will write this, what is the function whose derivative is 1, that is u. That means actually antiderivative we are considering, formula of integration. So that is u. And what is the function whose derivative is cos 2u, that is sin 2u divided by 2, means actually the integration of cos 2u, that is sine 2u divided by 2, and the upper limit, lower limit is 0, the upper limit is pi by 2, and thus we can evaluate this by putting the upper and lower limits. So, this is pi by 2 plus sine 2 pi by 2, that is sine pi divided by 2, this much is the upper limit, minus the lower limit is 0 plus sine 0 divided by 2, and we know sine pi is 0, sine 0 is also 0, and therefore this is equal to 2 into pi by 2 only. The remaining terms are 0, these are 0, and that is pi. So, thus I is equal to pi, and so therefore we have used the method of substitution to evaluate this integral. Actually, theorem number 10 we have used, and the substitution we have used is x is equal to pi of u, which is equal to 2 sine u. So, in this way the theorem can be used, and we are already using this theorem. So, one more example I want to state you that which will be from earlier type also. So, evaluate or show that, it is actually show that result 2 pi square by 9 is less than or equal to integral pi by 6 to pi by 2 2x divided by sine x dx is less than or equal to 4 pi square by 9. So, how to show this result, that we will see. We can consider x between this range. So, the solution for this is, let here we have x is between pi by 6 to, the interval of x is pi by 6 to pi by 2, and because we shall take the sine ratio throughout, and because sine function is increasing in pi by 6 to pi by 2, sine function is increasing in this interval, therefore we can write, and this implies, or sine pi by 6, sine pi by 6 is less than or equal to sine x is less than or equal to sine pi by 2. This we can write because sine is, since sine x is increasing in this interval pi by 6 to pi by 2, may not be written for other intervals, that we have to check. And what is the sine pi by 6? That is sine 30 is half. Half is less than or equal to sine x and is less than or equal to 1. Sine pi by 2 is 1. And now we take the reciprocal, and therefore this will be, if you take the reciprocal, 2 is less than, or you can write taking reciprocal, the inequality reverses. See what will be the inequality. So, this theorem is used for earlier example. We are not going to use this theorem for this example, but this is another example, and that I want to solve this example or state this example for you. And taking reciprocal, what will be this? So, we will get 2 is greater than or equal to, the inequality reverses, 1 upon sine x and is greater than or equal to 1, or that is, we can write this in reverse way, 1 is less than or equal to 1 upon sine x is less than or equal to 2. And now see, we are why we are writing this, to get this term, middle term, as 2x upon sine x. Now we multiply by 2x, and that is, this implies 2x is less than or equal to, because x is positive, therefore if you multiply by 2x, the inequality remains the same, 2x divided by sine x and is less than or equal to 4x. Now integrate this throughout, that means integral from pi by 6 to pi by 2, 2x is less than or equal to the same integral of 2x divided by sine x dx, should write dx here, and is less than or equal to integral from pi by 6 to pi by 2 of 4x dx. And we know the integration of 2x is x square, because derivative of x square is 2x, and therefore this will be x square, and the limits pi by 6 to pi by 2 is less than or equal to, we keep this middle term the same, because we want to find the limit for this integral, and this will be, see, we can take 2 outside and we can write this as x square. it is 2 into 2x, integration of 2x is x square, again this is pi by 6 to pi by 2. Now if you put the upper limit as pi by 2, then we get this as pi by 2 square, that will be pi square by 4 minus the lower limit is pi by 6, pi square by 36 is less than or equal to integral of this pi by 6 to pi by 2, 2x divided by sin x dx, and is less than or equal to, this is double of this, twice pi square by 4 minus pi square by 36. Now you can verify this is exactly the same, 2 pi square by 9, because if you take the 36 as the LCM, then 9 pi square minus pi square is 8 pi square divided by 36, and that is same as 4 by 9 dividing by 2. See, what we have to consider here is we have to divide by 4, and that means it will be 2 by 9. So check it, 2 pi square by 9, and that is double means it will be 4 pi square by 9. So this this inequality we have obtained. So in this way this type of problems can also be solved. So this is about the fundamental theorems of calculus. Thank you for watching the lecture.